Welcome to the deep dive. Get ready, because today we're plunging into something really fascinating. The surprising place where cutting-edge AI meets one of humanity's oldest puzzles, figuring out cause and effect.
That's right. We're digging into some, well, really interesting work. It's based on a presentation and a paper involving researchers, including some from Microsoft, looking at how large language models, LLMs, are starting to tackle the incredibly complex world of causal reasoning.
And our mission here really is pretty simple, to unpack what they found. How are these massive AI models being used to grapple with that fundamental challenge, pinning down the why behind things we observe?
Because, we've all heard the old saying, correlation doesn't equal causation. It's like drilled into anyone doing science or even just trying to make sense of the news.
Absolutely. So the big question this work gets into is, can an AI actually, learn to tell the difference?
Let's unpack this. The core problem they highlight is, well, it sounds straightforward, but it's profoundly difficult in practice, just because two things happen at the same time. Or maybe they seem to increase or decrease together, doesn't automatically mean one caused the other.
It sounds so obvious, but it trips us up constantly. Think about those classic examples they bring up in the material. You see a spike in shark attacks, and at the exact same time, ice cream sales just go through the roof.
Perfect correlation. But thankfully, ice cream isn't actually luring sharks.
Right, it's the shared cause, the underlying thing. Summertime. Warm weather sends more people to the beach, more potential interactions with sharks, and also makes everyone crave ice cream. Simple.
Or remember that study from years ago about nightlights and myopia in children?
Oh yeah, I remember that one.
Initially, it looked like kids who slept with a nightlight were, more likely to become nearsighted.
Which is a pretty scary thought if you're a parent.
Totally. But as later research showed, that the guy discussed here, there was a common cause at play there too. Parents who are myopic themselves, they tend to use nightlights more often.
Oh.
Maybe they read later or work, needing the light. And myopia often has a genetic component. So the myopic parents pass on the genes and use the nightlight, creating that correlation in their kids without the light itself causing it.
They even bring it right up to today, looking at examples from the COVID era. Sometimes analysis of CT scans trying to detect COVID actually ended up picking up on, well, other things like patient position or age.
Exactly.
Yeah.
It wasn't the scanner really measuring COVID symptoms directly as much as reflecting hospital protocols. Very weak patients might be made to lie down, that's position.
Right.
Or children were less likely to have severe COVID than adults, that's age. These factors correlated with whether someone was likely to have severe COVID, and so the scanner output correlated with them, but it wasn't isolating the disease itself.
So what all these examples really hammer home is that historically, untangling these messy relationships, figuring out the true causal arrow, well, that required deep human expertise.
Yeah, you needed a doctor, a biologist, maybe a physicist, a sociologist, someone with real specific knowledge about the domain to reason through the possibilities.
And that gets right to the heart of the challenge for AI, doesn't it? Working with causality, especially trying to build these things called causal graphs.
Yeah, complex maps showing how many different variables influence each other.
That's been a huge hurdle for machine learning models.
And they highlight two main difficulties here. One is that, frankly, human experts are still better, particularly with really complicated sets of variables or trying to pull causal information directly from unstructured text, think scientific papers, doctor's notes, that kind of thing.
Makes sense.
The other thing is that even these really powerful models like LLMs, they can still make unpredictable errors. They don't always reason the way we do.
Which is why the goal this work sets out isn't really about replacing human experts, is it?
No, not at all. It's more about combining LLMs with existing rigorous causal methods to potentially speed up and enhance causal analysis across all sorts of scientific fields. Think of it like giving experts a powerful new assistant.
Okay, so how do they actually start testing if LLMs could handle these causal tasks? Where do they begin?
They began by looking at something simpler, pairwise relationships.
Yeah.
Just two variables, A and B. Can the LLM figure out if A causes B or if B causes A or maybe neither?
Right, the basic building block.
Exactly. They use a specific set of tests, the pairwise relation distribution benchmark. It has over 100 pairs of variables from incredibly diverse areas, everything from biology to engineering.
And they tried different ways of asking the LLM.
Yeah, like asking, does A cause B in one go? Or maybe breaking it down into separate questions like, does A cause B and then does B cause A?
Yeah.
Trying different prompts.
Okay, and the results. This is the interesting part.
Yeah, here's where it gets really interesting. When they put GPT-4 to the test on this specific benchmark, it achieved an accuracy of 97%.
97%. On just figuring out the causal direction between two things across all those different fields.
Yep.
Wow, that seems dramatically higher than previous models. Weren't they around 83% or something?
That's right. The previous best data-driven models were at 83%. And this really highlights a key distinction they bring up in the work.
Which is?
Well, those older data-driven methods would look at large data sets of actual measurements, like paired numbers for altitude and temperature readings, and try to infer the directionality purely from the patterns in the data itself.
Right, like noticing higher altitude generally means lower temperature, so you infer the likely cause from that numerical pattern.
Exactly. But these LLMs, which they describe here as knowledge-based, seem to be doing something, well, different. They appear to be tapping into the vast amount of text they were trained on.
So the stuff they read.
Yeah, information about how the world works that's just embedded in billions of sentences. They describe it almost like fact remembering or retrieval. It seems less about crunching the numbers in front of it and more about accessing this huge store of background knowledge.
That is kind of mind-blowing. It suggests they've somehow absorbed some fundamental understanding of causal relationships just from reading the internet, basically.
It does seem that way, at least for these pairwise tasks. But, figuring out the relationship between just two variables is one thing. The real beast is what they call full causal graph recovery.
Mapping out all the connections when you have many, many variables interacting.
Precisely. And trying to do that just by combining all the pairwise results. That can lead to really messy, overly dense graphs. They mentioned one research project where this actually happened. Suddenly, everything seemed to cause everything else, which is very helpful.
Yeah, sounds like noise.
Right. Recovering those full, sparse, accurate graphs requires much more sophisticated techniques. And it often relies on big assumptions, like something called causal sufficiency.
Causal sufficiency. What's that again?
It basically means assuming there isn't some unmeasured outside factor influencing multiple variables in your graph that you don't know about, which could be messing up your analysis.
Assuming you've got all the important players accounted for.
Essentially, yes.
Right.
And it just makes you appreciate how hard this has been historically. Even figuring out the directionality between just two variables using pure statistics was incredibly tough back in the day. It took some really, as they put it, ingenious ideas from researchers years ago to overcome those limitations long before we had these massive data sets or these powerful LLMs.
Okay, so 97% accuracy on pairwise is amazing, but it's not 100%. Where are these LLMs still stumbling? What makes up that roughly 3% error rate?
Well, they point to issues with what they call ambiguous features. Basically, the LLM can get confused by vague language in the input prompt.
Can you give an example?
Sure, like asking about ozone concentration and radiation. You might get a wrong answer initially, but if you clarify it to ground level ozone concentration, which has a known relationship, then it gets it right.
Ah, so you need to be really precise with your prompts sometimes. It's not magic.
Exactly. It might even take a few tries, refining the question, which they noted was a bit surprising to some. You can't just ask one vague thing and expect perfect causal reasoning every time.
It sounds like that initial response, if the input's fuzzy, might be more like the LLM pulling a sort of stereotype from its training data, rather than truly reasoning about the specific situation.
That seems to be the idea, yeah. It defaults to common patterns. It's seen if the query isn't specific enough.
Okay, what about novel data? Information the LLM definitely hasn't seen during its training. Can it still figure out causal relationships in that context?
That's a great question, and they tested this. They used a dataset focused on neuropathic pain. And the prompt wasn't just a list of variables. It included details, even tables of data, describing things like left C3 radiculopathy or right adductor tendonitis, sometimes with known relationships already mixed in.
So the LLM had to use its general background knowledge plus this specific new data provided right there in the prompt.
Exactly. It had to integrate both.
And the results there?
Again, remarkably high on this specific novel dataset GPT-4, got near 97% accuracy again,
Wow.
which suggests they can actually integrate new information provided in the prompt with their existing knowledge base, at least for this kind of causal inference task.
Okay, that's impressive for reasoning. But they also tested its ability to use novel data for other tasks, right? Like just recalling information from new tables.
They did, like
Yeah.
filling in empty cells and tables containing information it hadn't seen before.
Mhm.
I think there was a data set about tubing manufacturing or something.
And how did it do there?
Well, the accuracy dropped significantly, something like 61% accuracy for filling individual cells correctly, and only 25% for getting a whole row right.
Mm.
So this tells us that while they can process and integrate novel data for causal inference pretty well, tasks like precise data retrieval or table completion based only on that novel data, well, those still present challenges. It's not a perfect recall machine just for new inputs presented that way.
Okay, so thinking about all this, the successes, the struggles, how can we actually start putting LLMs to work in the world of causal analysis? What are the practical applications?
They suggest several ways LLMs can assist human experts. One big idea is generating candidate causal graphs.
So not the final answer, but possibilities.
Exactly. Not graphs you blindly trust, but potential structures, maybe hypotheses, for a human expert to then review, validate, modify, or even discard.
Kind of like brainstorming for complex problems, but with an AI partner.
Precisely. They could also potentially critique existing graphs that a human has drawn, maybe spotting a connection the expert missed, or suggesting a missing variable, a potential confounder.
And I could see them being really helpful in the early stages of designing a study, right? Like you feed it your proposed variables.
Yeah, and it might suggest potential confounders you need to control for those variables that confuse the issue by influencing both your supposed cause and effect.
Or maybe suggest instrumental variables, those clever variables that can help isolate the true effect you're interested in.
That's another possibility they mentioned. And this is a really critical point, they emphasize repeatedly, human validation is absolutely essential, especially in high-stakes situations.
You mean like
Sensitive psychological cases or critical engineering systems or medical diagnoses, you don't just let the AI make the final call.
So it's about augmentation, not automation, at least for now and probably for a while in complex fields.
Definitely. And they make the point that even human experts don't always know everything. So combining their deep domain knowledge with the LLMs, let's say, vast pattern matching and knowledge retrieval capabilities seems like the most promising path forward.
Interesting. They mentioned something about a Python library too.
Oh yeah, that was a nice touch.
Yeah.
They mentioned the development of a Python library specifically for doing text-based causal analysis. It's kind of an homage to Judeo Pearl's foundational work in the Book of Why, which is, a landmark text in causal inference.
Very cool. Now, speaking of foundational concepts, the work also looks at whether LLMs can handle some key causal primitives, like the basic building blocks of causal reasoning itself.
Right, like understanding different types of causality. Can it distinguish between, say, population-level causality?
Like, does smoking cause cancer in general?
Exactly. Versus the actual cause for a single specific event. Did smoking cause this specific person's cancer? Which is a much harder question.
Or handling causal context, knowing that a cause might only lead to an effect under certain conditions, and distinguishing between necessary causes and sufficient causes.
Yeah, and the logic gate analogy they use is actually really helpful here. Think about an AND gate in electronics.
Yeah.
You need both input A and input B to be true for the output to be true. So A is necessary.
Yeah, we love electronics examples, but yeah, I was trying trying to stick to medical, biomedical data,